The force of gravity is all around us, and since ancient times its effects have been studied. In spite of this, it was not until the 17th century that its effects were mathematically quantified. Astronomer Johannes Kepler was the first to successfully model planetary orbits to a high degree of accuracy, publishing his laws in 1605. Many different objects in our solar system orbit around the Sun because of its strong attractive gravitational force, from planets to comets. There are several kinds of orbits, and they depend on a variety of factors specific to a given system. These can include the mass of the central body and the radial velocity of the orbiting objects.
So what kinds of orbits are there? We're considering a Keplerian orbit, one in which, other than the gravitational field of the central body, all the other forces are ignored. Now there are two main types of orbits, an open and a closed orbit. A closed orbit is one where the orbiting body eventually returns to its original position. It repeats over time. On the other hand, an open orbit extends to infinity and doesn't repeat. The family of curves that describes Keplerian orbits are called conic sections.
Conic section is a curve that is formed by the outline of the intersection between a plane at varying orientations with a cone. If drawn on a cone, we can see four different shapes, here representing four different orbital paths. These are circular, elliptical, parabolic, and hyperbolic orbits. Let's try to understand the mathematical geometry behind the shape of these orbits.
Elliptical orbits. An elliptical orbit is a closed orbit. If we draw this and label a focus, we can define the semi-major and semi-minor axis. If we draw a line parallel to the semi-minor axis outside the orbit and draw lines from different points of the orbit to this line is called the directrix. The distance from one of these points on the orbit to the directrix over the radius at that point is a constant ratio E, called the eccentricity. This is a defining feature of any conic section. The eccentricity describes the shape of the ellipse and can be geometrically described using a simple equation. For an ellipse, the value of E ranges from 0 to just below 1.
Circular orbits are a special case of an elliptical orbit where E is equal to 0, which you can see means the semi-major axis and the semi-minor axis are equal. An example of this is an artificial satellite orbiting around Earth. A parabolic orbit is a crossover point where a closed orbit becomes an open orbit. For this orbit, the eccentricity is exactly equal to 1.
Hyperbolic orbits. A hyperbolic orbit is another type of open orbit where the eccentricity is greater than 1. An example of a hyperbolic orbit is a comet passing by the Earth, but travelling too fast past the Sun, and it will never come back. Kepler's laws. Until around 17th century, it was generally acknowledged that the planets orbited in a perfectly circular orbit. However, in 1601, Kepler looked at the precise observations of the planets made by Tycho Brahe. He tried to fit Brahe's measurements of Mars's orbit into a circle, before he realised that it wasn't possible. And then in 1609, Kepler published his 3 laws of planetary motion.
The first law states that all planets in our solar system move in elliptical orbits with the Sun at the focus. The second law states that the radius vector of an elliptical orbit sweeps out equal areas in equal times. This means that the line connecting the Sun and a planet sweeps out area A at a constant rate. In other words, angular momentum is conserved. We can show this by drawing a small section of an orbit. In a small time dt, the planet sweeps out the triangle shape of area dA, which is equal to a half times r squared d theta. If we divide both sides by a small change in time that it takes to sweep the area, we get the constant rate, which is equal to half r multiplied by the angular velocity. If angular momentum L is equal to mass times r times angular velocity, we can put this into our constant rate equation to find that angular momentum is conserved, as the constant rate is equal to half the angular momentum over the planet's mass.
The third law states that for an elliptical orbit, the period of orbit of a planet around the Sun squared is proportional to the semi-major axis cubed. However, in a simpler circular case where E equals 0, this law is modified to state that the period of rotation squared is proportional to the radius of the orbit cubed. This can be simply proven by equating Newton's law of gravitation to the centripetal force.
The limits of classical orbits. Kepler's laws help us to understand the orbits of one body around another. In reality, every object in our solar system exerts a force on every other object because every other object with a mass has an attractive gravitational force. There are only special cases in which we can analyse this, for example if there are 3 bodies and one is significantly smaller than the other 2, like an asteroid in the Earth-Sun system.
Classical gravity is still used today, sending spacecrafts around the solar system and beyond. But Einstein's relativity is the accepted theory now, describing observations better than Newtonian gravity. An example is that Mercury's orbit shows behaviour not predicted by classical gravity. That behaviour is the unexpected rate at which the orbital axis of Mercury changes orientation. It was only general relativity that resolved this problem. Also, Newton's laws describe instantaneous action between masses, but relativistic gravity requires action to have a finite speed, which is the speed of light. But that's for another day. Thanks for watching, like and subscribe.